This is my screencast reassessment assignment for conceptual objective number 5C. The problem says a small car exits an expressway on a section of circularly shaped ramp that is banked at an angle of 21.5 degrees. The ramp has a radius of curvature equal to 49.7 meters. Suppose that the ramp is completely covered in ice so that you can neglect the effects of friction. If the mass of the car and driver is 1,550 kilograms, what constant speed must the driver maintain in order for the center of mass of the car to stay in the center of the ramp? So for part A, I drew a picture. The car goes up this ramp and curves around and comes out this end. So it tells you the radius is 49.7 meters, and then the mass is 1,550 kilograms. Then the angle is 21.5 degrees, and then my coordinate system is positive x is to the left instead of to the right. So I drew a free body diagram, and the car is going up the ramp, so it's going up to the left, so the ramp is sloped that way. And then this angle of this ramp right here is 21.5 degrees, and then the angle that the weight of the earth acting on this car is the same as the angle over here. So the only forces acting on this car are the force normal going perpendicular from the car and the ramp, and then the weight of the earth is going directly downward. So then I found the weight of the earth, which is equal to mg. So the mass was 1,550 kilograms, and you multiply that by 9.81, and I got the weight of my earth to be 15,205.5 kilograms per meters per second squared. And then, so for part A, it asked you for the speed. So the physical principle over here is Newton's second law, which is the sum of the forces equals m times a. So in order to find speed, you first have to find the force normal, because that helps you find the sum of the forces in the x direction. So you start with the forces in the y direction. So for my free body diagram, the only forces in the y direction are the force normal and then the weight, the one component of the weight of the earth. So this component right here, and then the force normal component. So if you plug those in to some of the forces in the y direction equals to ma, you get force normal cosine of the angle, which is over here, the cosine of that angle, which is the same thing as the 21.5 degrees, is in the positive y direction, and then in the negative y direction is the component of the weight of the earth. So you subtract that since it's going negative y, and then it should equal ma, except for you can assume that the right half of the equation equals 0 because it's not accelerating at that time. It's asking you for velocity, so the acceleration is just 0. So the right half of the equation equals 0, and then you can bring the weight of the earth over onto the right side, and then solving for force normal, and then plugging in, this is the equation you get for force normal, and then plugging in what you know, you have 15,205.5 is the weight of the earth, which you calculated before, and then cosine of the angle is 21.5 degrees. So the force normal comes out to be 16,342.7 newtons. So then that helps you get what you need to solve the sum of the forces in the x direction, and velocity, or the speed, is what you're actually trying to find. That's in the x direction, so that's why you need force normal. And then the sum of the forces in the x direction equals mass times acceleration in the x direction. Sum of the forces in the x direction equals mass times the centripetal acceleration, and that's just because this is a circle ramp. And then centripetal acceleration is equal to v squared over r, so I just plug that in. And then if you look at all the forces in the x direction, there's actually no forces besides the component of the weight of the earth right here, and because the rest of them are y, so we just calculate that as a y, that is a y, and then this is the only one we have left. So all the whole left hand side is just that component of the weight of the earth. So this line right here is the component of the weight of the earth, but this is also the same as this over here, this line. So I just used that instead. So I used the force normal because I have the force normal. The force normal times the sine of theta is the same thing as this line, but it's also the same as this line. So I just use this one. And then, so that's the left hand half. And then we found the right hand half by plugging in the v squared over r. So then I just set them equal to each other because that's what sum of the forces equals m times a means. And then simplifying it down, I simplified force normal into kind of what symbols or what makes it up. So then the force normal is just the weight of the earth down here, and then you multiply or you divide by cosine of the angle. So I plug that in here, and then you multiply that by the sine of theta, you just bring it down. And then on the right half you just have m times v squared over r again, and then since you have m on both sides you can cross them out and they cancel each other. So sine over cosine simplifies to tangent, and then you just have gravity in the numerator still. So g times tangent is that simplified down, and then since you crossed out the mass you get v squared over r. And then you want velocity, so if you multiply by r onto this side and then square root the whole thing, you get velocity. So plugging in what I know, gravity is 9.81, the radius was the 49.7 meters, and then the tangent of the angle was 21.5 degrees, and you square root the whole thing and you end up getting the velocity, or it asks for the speed, is 13.9 meters per second, and that is for part A. And then for part B, it says if the ramp is not icy, then static friction will act on the tires to prevent the car from skidding off the ramp. If the car enters the ramp with a speed higher than the speed you calculated, which way will the friction force point if the car does not skid? So for part B, I drew a new free body diagram because it's the same exact situation, but now you're adding static friction to it between the tires and the road. So in this case, you're trying to find, there's no friction because of ice. So the velocity I found was down here, and that was actually, since there's no friction, and in the real world there actually is friction between your car and your car tires and the road, that's the fastest speed, or like that's the perfect speed you can go around that curved ramp with no friction. So if you add friction now, that's going to change how fast or how slow you can go on that ramp in order to stay on it. So 13.9 meters per second was the perfect speed calculated. So if friction is added now, it just increases the range of the speed that your car can go on that ramp without falling off, because without friction up in the first part, if you were to go more than 13.9 meters per second or less than that, you would either go off the ramp if you were to go faster, or you would fall in to the middle of the ramp and that was if you were going slower than 13.9 meters per second. So for this, if you were just to add friction, friction is just what keeps you on that ramp if you're going faster or slower than 13.9 meters per second, and there is a limit to that. You will fall off one way or the other if you do go too fast or too slow, but friction is what keeps you on there. So which way will the friction force point? The force of friction, and it's static, will point just down the slope. It's always going to be, since it's circular, the best way to say it is just down the slope, but it's going to follow the car and keep on being like right behind the car so that you stay on the ramp. And then the car's not going to skid, it says. But for part C, it says, how does the speed you found in the first part change if the vehicle is a large truck where the mass is 3 times the mass of the car? So for part C, I wrote, mass doesn't change the answer, and that's because in the equation working it out in part A, you canceled the masses out over here. So if you cancel out the masses, then mass doesn't matter. So if you do the same thing with a truck that's 3 times the mass, it's not going to change the answer because you cancel it out and it doesn't factor into the actual velocity of the speed of that the truck or car can go. So then the mass doesn't matter at all.